So we're going to continue with shortcuts for taking derivatives that are going to make a few things easier. And we are going to talk specifically about the product and quotient rules. And the first one is the product rule. If you are multiplying two functions and you are asked to take the derivative, you're going to do the first function times the derivative of the second plus the second function times the derivative of the first. Now, when you're trying to remember this, I always tell myself 1d2 plus 2d1 as I'm going through this. So here's my 1, and here's my 2. So when I find h prime of x, I tell myself 1 d2, so the derivative of 2 is just 9, plus 2 times the derivative of 1, or d1, so 2 times x. And I go ahead and simplify. So 9x squared, and if I distribute, I get 18x squared plus 4x. And I can simplify that to get 27x squared plus 4x. And we're done. Okay, so again, 1 and 2. So find the derivative. Y prime equals 1 d2, so 3 halves x, and then if I minus 1 from there, I get 1/2, and then the derivative of 1 is 0, plus 2 d1, and technically we're done. We're going to leave this as it is because it makes it a little easier to not have to simplify everything. 3, we have 1 and 2. Okay, so the derivative is 1 times d2 plus 2 times d1. And if you can simplify, you can. Otherwise, you leave it. Okay, the quotient rule. If you're dividing two functions and you want to find the derivative of the quotient, you can do 2d1 minus 1d2 over, sorry, I'm going to rephrase that. You can do the bottom times the derivative of the top minus the top times the derivative of the bottom over the bottom squared. When I do this, I say low d high minus high d low over low low. Okay, so f prime of x is low times the derivative of the high, which is just 1, minus high times the derivative of the low, which is 2x, over low low. So you can write it twice or you can square it. Now I'm going to simplify a little bit for this one. 1 plus x squared minus 2x squared gives me a final derivative of 1 minus x squared over 1 plus x squared, quantity squared. Okay, same thing here. Low times d high, so low stays the same, take the derivative of the high, minus high times the derivative of the low. Okay, so the derivative of e to the t is just e to the t. Derivative of t is 1, so I get plus 1 there, over e to the t plus t. I wrote that wrong. That should be a t there too. And square it. And then we could do quite a bit of simplifying. I'm actually going to factor out an e to the t power, so I'm left with e to the t plus t from this first group of parentheses, minus e to the t minus 1. So really I distributed that negative through here, pull that e out, and then I can simplify a little bit further. So the derivative is going to be e to the t, these cancel, times the quantity t minus 1 over e to the t plus t, quantity squared. As far as EP is concerned, if you got to this here without simplifying, and you could use it correctly in your free response questions, you don't have to simplify. Okay, next one, tangent line. Same process. We're just using the quotient rule though because there is a quotient here. So low D high minus high D low over low low. And I'm going to tell you again, you don't have to simplify this. If we do f prime of 1 and plug 1 in here, I get 5. If I plug 1 in here, I get 7. So I have 5 times 7 in the top. Minus, here I get 3, 4, minus 2 is 2. And 12 times 1 is 12. And then on the bottom, 4 times 1 is 4, plus 1 is 5 squared. So if I simplify, I get 35 minus 24 over 25, which is 11/25. So this is my slope. And then I'm also going to plug this into the original function so I can find my y value. So f of 1 gives me 3 plus 1 minus 2 over 4 plus 1. So 4 minus 2 is 2 over 5. So we're going to do y minus 2/5 equals 11/25 times x minus 1. This is a tangent line. The last one's a little bit more complicated because it's an application problem. The power that a battery supplies to an apparatus, such as a laptop, depends on the internal resistance of the battery. For battery voltage V and internal resistance R, lowercase r, the total power delivered to an apparatus of resistance capital R is P equals V squared R, big R, over big R plus little r squared. Okay, we are going to treat this and this as a constant. Those are like numbers there, so we're not going to worry about derivatives. We're going to find dp over dr by doing low d high minus high d low. Okay, so this is the same as saying this in the denominator. Okay, so low doesn't change, so I'm going to keep that r plus r quantity squared times the derivative of high. This is a number in front of r to the first, so it's really just v squared, minus high. And now I'm going to use this down here for my derivative. We're going to have 2r plus 2 little r over big R plus little r. Instead of squared now, it's going to be to the 4th power because we had to square that. Okay, I'm going to erase this work and come back to this. We're going to simplify here. In the numerator, if I have r squared plus 2 big R little r plus little r squared, well, times v squared, I'm going to simplify. Squeeze a 2 in here. So 2v squared big R squared plus 2v squared big R little r. I'm going to distribute. And that should be a negative there because it was a minus in between. So we're going to cancel some stuff out here. So notice that this here cancels with that there. And if I simplify this, I get v squared r squared minus v squared big R squared, which is v squared times r squared minus big R squared. And that's v squared times little r plus big R times little r minus big R. So this will end up being 0 when r equals r. So if r minus r equals 0, it's going to happen when they're equal to each other. Okay, I'm not so concerned with this. It's just a good application problem to practice. There's your summary. There's your practice. Don't worry about 62. If you have any questions, let me know.